Hi everyone, this is Dr. Hopkins recording the next in our series of videos for 472. In this one we're going to talk about electrolytes in solution, the thermodynamics of them. Okay, so let's set up our situation here. We have electrolytes, so what we mean is something that's charged in solution or conducts electricity. So for example, a salt, an acid, or a base are all examples of electrolytes. So let's add some kind of salt and allow the ions or allow it to dissociate into a cation and anion. Okay, now if we have a neutral salt, we know that the stoichiometric coefficient of the cation times the charge of the cation equals and is opposite to the stoichiometric coefficient of the anion times the charge of the anion. Okay, so we would have that kind of situation. And if we were to dissolve a certain number of moles of the salt in a certain number of moles of solvent, we have N plus, so this is number of moles minus the undissociated. If it's not a strong electrolyte, then it won't completely dissociate, so we need to account for the undissociated. So we have our moles of cations and anions discussed. So if we have a strong electrolyte, then this N sub U is equal to 0. So we have none of that. All right, so let's set up. If we want to know the thermodynamics, we need to know the chemical potentials of all of the components. So in this case, we have the chemical potential of the cation is just the partial molar Gibbs free energy of the cation holding everything else constant, the anion and the solvent, and then if it were weak, it would be the undissociated, which we would have to add a fifth term in all of these partial derivatives. Okay, so the chemical potentials of all of the components. And if we want to know about the thermodynamics of that process, we would evaluate the overall free energy or Gibbs free energy. And so we'd look at how the chemical potential changes with the Gibbs free energy changes as we change the number of moles. So we're going to set a couple of conditions. Let's consider a strong electrolyte, so we'll get rid of our undissociated. And we're going to just say it's a dilute solution, so that the total number of moles is just the total number of moles of solvent. Okay, so we're not going to change the number of moles of solvent. And then we'll look at our chemical potentials. So then we're left with just the chemical potentials of the cation and anion. We have stoichiometric coefficients according to the ratio of the salt. And so we can now set out a more general expression in terms of activity for our cation and anion. Remember, anytime we set up a chemical potential, we have a reference state. So this would be this standard state. We have our activities. And in this case, we're not going to set it in terms of mole fraction. With solutions, we're going to use molality. So this is the activity coefficient of the cation times the molality of the cation over some reference molality. And now these M naughts are all 1 mole per kilogram concentration. And so we have activities and so forth. So our activity coefficients, if it were 1, then this is just the ratio of the molalities, or it's just the natural log of the molality itself if we divide it by 1. All right, so then let's set up we'll add both of those chemical potentials together, multiplying by the stoichiometric coefficients, and then this part we're going to collapse together into one standard state chemical potential, such that we just have our nu plus and then this nu, and we've divided, assuming that mu of that mu plus naught, mu minus naught is 1. We've simplified our expression overall for the chemical potential to this. Okay, now we know that the cation and anion are not independent, right? They're going to dissociate dependent on each other. We don't just add a cation and then add the anion at a separate time. They dissolve in solution at the same time. So we can set up our activity coefficients and our molalities together. Okay, and so I've carried my my stoichiometry through my natural log. So we've set these up, right? And then we can pull the RT out, and we just have this. We've redefined our combination of activity coefficients into this gamma plus minus and this m plus minus, recognizing they're not independent. So we only need to write one activity coefficient, which is this mean of ionic of these activity coefficients and the mean of these molality ionic molalities as well. So we have these set up so that our chemical potential is referenced to a reference state. We have our overall stoichiometry, and then RT is the natural log of this mean activity coefficient, or mean ionic activity coefficient, and then the natural log of the mean ionic molality. So this is the ideal, this is the non-ideal contribution. Okay, so how do we determine an activity coefficient in this case? And we can rely on, we know we have charged species, so we have now the idea of Coulombic interactions happening in solution. But let's set this up. So we have our activity is our mean ionic activity is the combination of the mean ionic activity coefficient times the mean ionic molality. Okay, set up according to our ratios and so forth. And then we're going to apply the Debye-Huckel limiting law, or Debye-Huckel model, to these dilute electrolyte solutions. So I'm not going to go through and derive how we got to this point, but basically, theoretically, based on Coulombic interactions, we set up that the natural log of this activity coefficient, the part we don't know, we can measure the ionic molalities. We know that based on the dissociation, is just minus, this is the product, the absolute value of the product of the charges, right? So if they're plus 1 and plus 1, that's just 1. But if it's plus 2 and minus 3, then we end up with a little larger value there. This I to the 1/2, which we'll explain in a minute, that's ionic strength. This is the, and I'm going to go ahead and reveal all these constants. So all of this is, so we have F to the 6, so that's the Faraday constant. This is the density of the solvent, 32 pi squared. This is the vacuum permittivity. Okay, it's given below. This is the relative permittivity, or the dielectric constant of the solvent. This is Avogadro's number, and then the gas constant times temperature. Okay, so that's a lot, but the important part is here we have the ionic strength is related to our molality times our charge squared plus the molality times our charge squared, and then it's 1/2 of that. And this reference is the 1 mole per kilogram. All right, so we can simplify that. There are a lot of universal constants in there that don't change, and make a more general model, and then we've switched it to the 10 base log at this point, but the log of the activity coefficient is this. This is the combination of all of those universal constants. We still have our charge term, we have our ionic strength term, but now we've collected all the terms that are related to the solvent itself, so the density, the dielectric constant, and the temperature. Now if we were to do this, we add these up for water at 298 Kelvin. We know the dielectric constant is 78.54, the density is 0.997, and then all of those constants end up in what's called an A term. It's 0.509. So this log of the activity coefficient is minus 0.509 our charge times our ionic strength. And this model is not a bad model for predicting the activity coefficient of electrolytes at very low ionic strengths, okay? Because what we have is we have large deviations from ideality because we have long-range interactions or long-range Coulombic interactions. We know that plus charge and minus charge see each other over long distances, and that plays a significant role in how these solutions behave. So what happens if we increase the ionic strength? Well, at that point, the long-range interactions become shielded because we have more ions in solution. So there's so many ions in solution that they're not seeing each individual ion. So we need to correct that Debye-Huckel model into what is called the Davies equation. And this is now for aqueous solution. I do not have this for a general solution, but you can imagine pulling that out. I just don't know how to correct this, but this is for aqueous solutions. So our activity coefficient, the log of our activity coefficient is that minus 0.509. Our charge, we have our ionic strength. We have a ionic strength in the denominator, and it's minus 0.3 times the ionic strength. Okay, so we get a slightly different value for our activity coefficients. And we can use that for moderate ionic strength. As you go to really high ionic strengths, it's a very difficult thing to model the activity coefficient generally. So until next time.